Muy buenos días, soy Oleida Suárez, secretaria de la Sociedad Mexicana de Ingeniería Geotécnica. Sean bienvenidas y bienvenidos a este evento especial en conmemoración del Día Internacional de la Mujer. Una fecha que nos invita a reflexionar sobre los avances, desafíos y oportunidades en la lucha por la igualdad de género en todos los ámbitos, incluyendo la ingeniería geotécnica. Hoy nos reunimos para reconocer el talento y la contribución de las mujeres en nuestra profesión, promoviendo el intercambio de conocimientos y experiencia que nos permitan seguir avanzando hacia un entorno más equitativo e inclusivo. Para iniciar, contaremos con una conferencia magistral a cargo de la doctora Shideh Dashti, una destacada investigadora y académica que nos compartirá su visión sobre nuevos enfoques en la mitigación de la licuación mediante metodologías basadas en físicas y datos. Posteriormente, llevaremos a cabo una mesa redonda moderada por la doctora Alexandra Osa, donde participarán 5 profesionales dedicadas a la geotecnia en distintas regiones del país. En este espacio compartiremos reflexiones sobre el papel de la mujer en la ingeniería geotécnica, los retos que aún enfrentamos y las oportunidades para fortalecer el liderazgo femenino en el sector. Les invito a participar efectivamente en este diálogo que busca inspirar, fortalecer y visibilizar la labor de las mujeres en nuestra disciplina. Gracias por acompañarnos en este evento que celebra el talento, la resiliencia y el impacto de las mujeres en la ingeniería y en la sociedad. A continuación, le cedo la palabra al doctor Miguel Mánica, presidente de la Sociedad Mexicana de Ingeniería Geotécnica. Adelante, doctor.
Muchas gracias, Yoleida, y muy buenos días y muchas gracias a todos por asistir a este importante evento. También muchas gracias a todas las que participarán en la mesa redonda, a nuestra conferencista y a todas y a todos los que participamos en la organización. Antes de comenzar, les haré una breve introducción de nuestra conferencista. Es para mí un gran honor presentarla. Es una colega y una amiga con una destacadísima trayectoria profesional y en investigación, quien demuestra la capacidad de las mujeres para destacar y contribuir al desarrollo de nuestra disciplina. Entonces, antes de cederle la palabra, me permitiré leer una breve semblanza de la conferencista. Shideh Dashti es profesora asociada en Ingeniería Geotécnica y Geomecánica en la Universidad de Colorado Boulder y directora asociada de Administración en el Departamento de Ingeniería Civil, Ambiental y Arquitectura. También dirige una iniciativa de investigación interdisciplinaria financiada por la universidad titulada Infraestructura Resiliente con Sostenibilidad y Equidad. Shideh obtuvo su licenciatura en la Universidad de Cornell y su maestría y doctorado en la Universidad de California, Berkeley. Trabajó brevemente en Arup y Bechtel en varios proyectos en Estados Unidos y otras partes del mundo, principalmente en el diseño sísmico de estructuras subterráneas, cimentaciones y taludes. Su equipo de investigación en la Universidad de Colorado estudia las interacciones e interdependencias entre sistemas de infraestructura durante terremotos y eventos climáticos extremos, el comportamiento sísmico de estructuras subterráneas, la activación, consecuencias y mitigación del fenómeno de licuación a escalas local y regional, el impacto de peligros climáticos sísmicos combinados en infraestructura y la intersección entre resiliencia, sostenibilidad ambiental y justicia. Recibió el premio Arthur Casagrande en 1918, en el 2018 y el premio Walter Hubbard de Investigación en Ingeniería Civil en el 2021, ambos otorgados por la Sociedad Americana de Ingeniería Civil, así como el premio a la Conferencia Distinguida 2025 del Instituto de Investigación de Ingeniería Sísmica en Estados Unidos. Shiden, muchísimas gracias por aceptar la investigación y por presentarnos esta muy interesante conferencia. Te cedo la palabra.
Solo recordar antes de que la doctora inicie con su presentación, en la parte inferior del menú de la plataforma Zoom tienen un globito para la interpretación. Ahí pueden cambiar entre los idiomas y tener la traducción simultánea. Muchísimas gracias. Adelante, doctora.
Thank you both so much. Can you hear me okay? And you have my slides, right? Okay.
So,
All
sorry,
right. Well,
can you go
okay.
to presentation mode because we cannot see in presentation mode.
It's not in
No,
presentation mode?
no, it's like No, we cannot see in presentation mode.
So it is for me. Okay, let me try again. So right now it's not in presentation mode,
Okay.
but now it is. Now
No,
it
but
is on my.
like it's like it opened in presentation mode
Oh,
and then returned to the non-presentation mode.
oh, that's very strange. Hmm. How do you suggest we do this?
Do you have another uh, monitor on your PC?
I can share this with, or maybe we can use the same slides that I sent Miguel. Or maybe I can just increase the size of it.
Yeah, if that works for you, it's okay.
So, do you see the screen right now? Like, is it full? Do you see full screen? I know it seems like it doesn't show full presentation mode.
No, I can
It's
no.
still
It's still yeah. Or maybe can you disconnect your other monitor from your,
this. Oh, this is just my laptop. It's not connected to a monitor.
or maybe can you close the presentation and open it again,
Okay, I will
please?
do that.
Yes, please. Thank
Sorry
you.
about this.
Do you have any videos? Because if not, the alternative could be to export it to a PDF and show the PDF in full screen.
She
I
has
have
one video.
one video,
Video.
but let me open it again. Interesting, because when we tried it, it worked.
Yeah.
It seems it's an issue of the computer because it appear in presentation mode for a second and then go back automatically.
Is it the same right now?
Yes, it's the
I think
same.
so.
Yeah,
So
but
we can go like that, like that. I think it shows in a good size as it is.
Okay, okay. So for me, it's presentation mode, but maybe we'll come back for the Zoom audience too. I hope. Um,
But what we
okay.
don't know if it's
Oh,
going to
oh,
advance
the video.
if you advance. No, it's better for you to get out of presentation mode so that we see the same than you.
Oh, so right now. Okay, so then that's going to be a problem because some of them are animated. So even now you don't see, do you see things moving?
No.
no.
Oh, wow. Okay. So let
Comentan
me maybe,
que le dé F11, varios aquí, Miguel. Con F11 al parecer se pone en presentación.
No, el problema es que se pone en presentación automáticamente se quita y nosotros vemos algo diferente. No, no es que no se esté poniendo en modo presentación.
let me leave and come back. One other option is Miguel, how about you running the slides?
Yes, I'm going to download them. The issue is
Okay.
I don't have Windows in my computer, so
But
I will have to.
is it the same presentation that you
It,
sent me?
Can you share
it
it,
should,
Marcos?
Yes, because I have it here.
Perfect. Perfect.
Just a second.
I can also leave and join back in.
No, it's not necessary.
No?
Peter. Just a
Okay.
second.
You can even share a control to her and she can advance them herself. Is that possible?
No,
No. Okay.
no, but you can tell me next time I'm gonna be here.
Okay. So you will have to tell him to advance the slides.
Okay, sounds good.
Perfect. So sorry everyone for these technical issues.
Yeah, I apologize. Okay, so I guess we can move to the next slide. Good morning, everybody. Thank you so much for this opportunity. And before I start and share my team's research related to liquefaction, I wanted to acknowledge the funding agencies, the centers, the collaborators, and also especially 3 of my former PhD students who made this research possible and whose research I will be presenting today. Now Professor Yu-Wei Huang, Dr. Caroline Bessette, and Liane Brito. Okay, next slide, please. Well, previous earthquakes have provided many examples of the damaging effects of soil liquefaction on the built environment, in particular in terms of excessive settlement or rotation of buildings on shallow foundation. The current state of practice, we could move to the next slide, the current state of practice for estimating the settlement of structures still relies heavily on empirical procedures that, if you click one more time, that estimate volumetric deformations in individual layers and ignore the presence of the structure altogether. And they add up essentially the volumetric strains in different layers to get the final total surface settlement, ignoring the mechanisms that are really existing below the structure under the influence of seismic soil structure interaction. Next slide, please. So previous earthquakes have provided many examples of how these procedures, these empirical volumetric strain-based procedures, are unreliable and unconservative when estimating the settlement of the foundation, because they ignore seismic soil structure interaction and the mechanisms of deformation that are active below the foundation compared to the soil in the free field. Next slide, please. And as a result, to address some of these gaps associated with building performance on liquefied soils, we in our team have developed the first probabilistic procedures for estimating both settlement and tilt or differential settlement, considering soil structure interaction or SSI in 3 dimensions, and all the mechanisms of deformation that are active based on 63,000 3-dimensional soil structure interaction analyses. These analyses have been validated with centrifuge experiments and adjusted based on case histories, and they consider all the tectonic environments when combined with our ground motion prediction equations, which is a significant improvement to the previous procedures that were only considering free field conditions that I showed earlier. Next slide, please. Now, these procedures have recently been extended to include triggering and mitigation as well. Next, considering new measures of demand and resistance, for example, cumulative absolute velocity, instead of surface PGA that is mechanics-based and accounts for the degree of softening that we are interested in within the deposit. Next, please. But there is one caveat to all of these procedures, and that is that they generally assume that we are dealing with uniformly layered, fully saturated deposits of clean sand, and that the buildings are essentially isolated. Next, please. So there are problems with both of these assumptions. First, these analyses typically assume an idealized soil profile, like I've shown at the top right corner of the slide, which are really a big gross simplification of the reality, which is the bottom of the slide. That's what the actual soil profiles usually look like. Soil's natural deposits are often highly stratified, and that stratification affects the extent and distribution of pore pressures and strains. And nevertheless, most of the procedures that we have available for liquefaction consider layers in isolation without accounting for cross-layer interactions. Even though case histories, for example, after Christchurch in New Zealand, have shown a significant amount of error in our estimation of liquefaction triggering when we don't consider cross-layer interactions in stratigraphically variable deposits. But we don't know the implications of this problem in our procedures in terms of displacements or in terms of effectiveness of mitigation strategies. Next, please. On the second assumption, so I mentioned our procedures, which are an important improvement to what we had before. They still assume that buildings are essentially isolated. But in reality, especially in urban areas, buildings are rarely found in isolation. We know, and there is plenty of evidence from case histories, that proximity and arrangement of structures impact the direction and magnitude of the displacement of the foundation due to what we refer to as structure-soil structure interaction, or triple SI. Next, please. Now, even though there is plenty of evidence that the triple SI has a significant influence on the response, this problem hasn't been sufficiently studied on liquefiable soils, and therefore our existing procedures for liquefaction, for the most part, actually ignore SSI, but definitely coupling between buildings is not considered in most of our design standards. Next. So the last thing I want to mention about gaps is that we live in a changing climate, and that means more intense and more frequent climatic hazards like floods, wildfire, drought, and these extreme events cause fluctuations in the temperature, moisture, and flow. They affect the state of stress in our soils, and they therefore affect dynamic soil properties due to soil-atmosphere interactions. And nevertheless, the impact of these fluctuations on soil liquefaction susceptibility, triggering, or consequence is understudied, especially soils that are variable in their degree of saturation, and where these fluctuations can make a significant influence in the amount of suction, stress level, and dynamic properties. Next, please. So to address some of these problems, we use an integrated approach that includes field observations, physical modeling, constitutive modeling, and numerical modeling to study some of these interactions. Next slide, please. So I use this kind of integrated approach in our team to study interactions between soil layers and the structure. For example, if you click next, between soil layers and structure, so that's soil structure interaction, or next between soil layers in stratigraphically variable deposits, or between structures through soil, or between mitigation strategy and next, this mitigation strategy and the performance of the soil and structure system. We also study the interactions between soil layers and the atmosphere, for example, under compound climatic hazards, and the interaction among this whole system and their influence on various sectors of our community. In this presentation, I'm only going to focus on next, how different soil layers impact the performance of the structure, and how mitigation impacts the response of the system in such conditions when we are dealing with realistically variable soil profiles with stratigraphic variability. Next. Okay, next slide, please. So here is an outline of the presentation. I will first talk about the methodology, and then we'll take a small part of our simulations to look at how stratigraphic variability impacts the efficacy of liquefaction mitigation. And then we will talk about machine learning predictive models of performance. Okay, so the next slide, we used the large centrifuge facility that we have available at the University of Colorado Boulder in the US has a radius of about 5.5 meters. And here we have the opportunity to build many models, scaled models of soil structure systems and study this phenomenon physically with variations in the soil profile, structure, and ground motion so that we can calibrate and validate our numerical models accordingly. Next slide. So we performed a large number of experiments, but here I'm showing the schematic drawing of a few of them where we had a layered liquefiable soil profile. In the middle, typically a deposit of loose, clean sand. Sometimes we added a thin silt capping layer above that critical layer. In some of the tests, we had no structure, no mitigation. Sometimes we introduced a form of mitigation. Here in this slide, I'm only showing one form of mitigation, that is dense granular columns, or DGCs. I will be using throughout the presentation for dense granular columns. And then some of the experiments had an isolated form of a building or a geotechnical structure like an embankment. Sometimes we also varied the thickness of the liquefiable layer to see the effects of that variation on the performance of the system. Next slide, please. Here are pictures of two structures that were typically used in these experiments. Structure A, the shorter structure, represents a 3-story building, and building B represents a 9-story building on a 1-story basement foundation. And these structures were designed with inelastic fuses, so they are capable of inelastic deformations, damage, and collapse. But they were designed for different seismicity levels in the state of California in a shallow crustal earthquake tectonic environment. Next slide, please. And here is a video, time-lapse video showing essentially how some of these experiments, these model experiments were prepared. If the video plays, yeah, there's a time-lapse, so it goes really fast. It gives you an idea for the size of the container that was using the centrifuge. We had an automated pluviator that was calibrated to achieve a certain relative density for dry pluviation of the sand layers in this case. Then we placed sensors at their designated locations and the structures, and then prepared the model to take it to the centrifuge where they were, the model was saturated and then spun up in the centrifuge, and then we applied the ground motion. Next slide, please. So in the next slide, I'm showing some of the properties of a sequence of ground motions. These properties are shown in prototype scale units, but in the centrifuge, in model scale, everything is different because of the scaling laws. Or accelerations are, in this case, 75 times more are scaled up in the centrifuge, and the time is scaled down. So everything is more intense and in a shorter duration in the centrifuge. But here I'm showing in prototype scale units what one of the main acceleration demands as a horizontal component of a broadband signal during the Kobe earthquake at the Port Island station. Now, in parallel to the centrifuge experiments, we performed numerical simulations. We used 3 different types of constitutive models that are appropriate for capturing soil response when it liquefies. Here I'm showing only one of the models, a pressure-dependent multi-yield surface soil constitutive model. This model has many parameters that were calibrated. Next slide, please. Using a sequence of monotonic and cyclic triaxial tests that we performed in our lab. Next slide. in addition to empirical data on number of cycles to liquefaction, but also we used one centrifuge experiment, next slide, where we had no building present and no mitigation, but we had a boundary value problem that could be used for calibrating the properties of our soil profiles under the expected confining pressures and drainage and the ground motion that we expected later in more complicated soil conditions. Then after calibration, we modeled the entire system, the soil foundation structure system with or without mitigation. Next slide. And we started to compare the results for our models with a structure or with an embankment, different kinds of mitigation or mitigation properties. And here in the next slide, I'm showing the a summary of some of these comparisons in terms of vertical displacement or horizontal displacement and tilt. Overall, we were able to capture these trends well. In the next slide, there are more details in terms of the excess pore pressure time histories, settlement, tilt, or acceleration response spectra. There's not enough time to cover all of that in our publications, which I will cite at the end. All of these details are provided in the publications. Next slide, please. So after this initial exercise of understanding the mechanics and using the physical models to calibrate and validate our numerical tool, we took this numerical model and performed a limited sensitivity study to see how important is stratigraphic variability in terms of building performance on liquefiable soils and in terms of efficacy of mitigation. So here I'm showing the results from this limited sensitivity study. That's just numerical models that were previously validated. I will only show the results for this one motion, just so that we can better see the trends. Now, in the next slide, I will show a few different soil models where we sequentially make the profile more complicated. So in model 1, on the left, we have a uniformly layered deposit of essentially clean sand. The critical layer is in the middle. That's a loose, saturated, clean sand deposit, and it's sandwiched between two denser sand layers that are not going to liquefy, but they also don't introduce much of a variation in permeability. In the second model, we introduce one thin silt layer above that critical liquefiable layer. In the third model on the right, we introduce multiple silt interlayers. So that's essentially dividing up the continuity of the critical liquefiable layer. In the fourth model, we take each of those critical layers and spread them out along the profile. In the fifth model, we vary the thickness of the critical layer. And all of these simulations were done with building A, that's the 3-story building on a mat foundation, and building B, that is a 9-story building on a basement foundation. And all of them run first with no mitigation, and then with DGCs or dense granular columns in different forms. So these DGCs, we have the baseline case with an area replacement ratio of 10%. Then we have, then we look at the influence of area replacement ratio by increasing it to 20%. We vary the stiffness ratio. We look at the possibility of clogging. What if it doesn't drain? What is the effect on the system? We also look at how densifying the soil around the DGCs, which could happen, depending on the soil type, depending on the energy of compaction of the DGCs during installation, we could get densification. How does that mechanism combined with drainage affect the performance? So we looked at these variations in our sensitivity study. Next slide. And then now we can look at how for each of these profiles, the performance changed. And here I'm only, for the interest of time, showing performance in terms of permanent average settlement of the foundation for the two structures in question, A and B. So at the bottom, I'm showing the average settlement of the foundation when not mitigated. In the middle, showing the permanent settlement when mitigated with DGCs. And at the top is the ratio of DGC mitigated to non-mitigated. And so the top one is essentially a result showing the efficacy of mitigation. How effective is it? And the lower, the better, because a lower ratio means we've been very successful at reducing the settlement of the building through mitigation. So as we see, we go from profile 1 to 2, depending on the structure, we see an increase in foundation settlement because the silt increased the generation of excess pore pressures. But as we go from 2 to 3, the addition of silt interlayers, depending on the building structure, could actually reduce the settlement of the non-mitigated structure by breaking up the continuity of the layer. But in this case, the DGCs were not very effective. Now, in the fourth model, we see a really poor performance from the DGCs. If you look at the top plot, the normalized value is above 1. That means mitigation amplified the settlement of the foundation. But to be fair, if we look at the response of the non-mitigated model, it's very small settlement in the non-normalized value. It's very small. And even the mitigated value, even though it's increased a little, it's still very small. It's within the design limit. So let's see what actually happened during this case. The next slide, I'm showing the excess pore pressure and shear strain contours. So this is a case where we have a thin liquefiable layer at depth. And the presence of that thin layer is essentially creating low and is essentially base isolating the layers closer to the foundation, in the vicinity of the foundation. And that is reducing the accumulation of shear strains in the vicinity of the foundation and is reducing the deformations. When we add DGCs, so the animations to the right, that's a case where the presence of DGCs are essentially redistributing the excess pore pressures and shear strains within the denser layers a little bit. And that is increasing the settlement of the foundation a little bit. But it's still within the design limits. And this is not something to worry about. But this is one case where I would have said, perhaps mitigation was not necessary. This is a case where we are getting sufficient base isolation because of the liquefaction at depth. And perhaps this is a case where we wouldn't have needed to invest in installing DGCs to help the building, at least in terms of the performance related to settlement. Next slide, please. Now, when we go to the last profile, this is a case where the thickness of the critical layer is variable. And we see that has led to accumulation of asymmetric deformations below the foundation. And that increased the settlement and especially the differential settlement of this building. However, DGCs here were successful at limiting those deformations in the profile. Next slide. So I will also just quickly show how the different properties of DGCs affected the mitigation efficacy in terms of the ratio of DGC to non-mitigated settlement. So this is the baseline case. Then when we consider clogging with the permeability ratios of 0 or 1, that's a case where we see really poor performance from mitigation. This shows that drainage is a very important factor in reducing settlement. Then later, when we add area replacement ratio we improved the performance. With stiffness ratio for this particular condition, things didn't improve that much in terms of settlement. But the best performance here was when densification was combined with drainage. So all of these results are detailed in our recent publication in the journal Geotechnical Geoenvironmental Engineering, ASCE. And we didn't only compare settlements here. I only showed settlement, but we also compared the performance and the impact of these variables on tilt of the building, as well as acceleration demand within the superstructure. And all of those are discussed within this paper, which I refer you to. But I'll move on so that we have some time to talk about predictive models. Okay. So now, after this initial calibration and validation, and this initial sensitivity study to get a sense for how important is stratigraphic variability, we now had an opportunity to take these numerical models and simulate more realistic conditions. Now we could vary the profiles quite a bit, introduce multiple silt and clay layers, interlayers, vary the thickness and continuity of our layers, vary the properties of the foundation, have more realistic structures, and see if we can generate the database that is required for predictive models of performance and predictive models for mitigating this hazard. Next slide, please. So this is the parametric study that was initiated last year, where we sampled the input parameters using quasi-Monte Carlo sampling that led to more than 19,000 single soil column simulations for nonlinear site response analysis, as well as 4,000 three-dimensional soil structure interaction simulations, all in open seas. And in all of these simulations, we monitored accelerations as well as shear deformations and excess pore pressures, ejecta deformations, with the goal of improving predictive models. Next slide, please. So this is showing the input parameters that were varied in terms of the soil profile itself and the stratigraphic variability in the soil types and configurations geometry that was considered, the properties of mitigation in terms of the DGC properties within the range that we expect in the field, of course, ground motion properties, as well as the foundation and the structure. For structure, we considered a range of reinforced concrete, steel, and wood frame buildings that are commonly built inside nuclear active areas of the United States. And then that led to 100 different model configurations. And we selected, using quasi-Monte Carlo sampling, 21 ground motions for each model configuration that was randomly selected. And for each configuration, we had one simulation with no mitigation and one with DGCs. That led to more than 4,000 SSI simulations that were performed in the finite element platform OpenSeas. Next slide. So just to put things in context, I have included the three major, papers that we published in our team, providing predictive models of performance, each of them for different problems. For example, on the left, Bullock et al. 2019, we provided predictive models for foundation settlement on liquefiable soils, but these were generally uniform and uniformly layered deposits of primarily clean sand. The second model, Tisnado et al., provides models of liquefaction triggering in free field conditions, but near dense granular columns. And on the right, Wang et al. 2022 provides models of foundation settlement on densified soils. All of these models used a simple form of machine learning called the lasso that is very close to a classical regression. to essentially find a functional form for predicting the demand parameter in question, like settlement or pore pressure, and so on. Using this kind of simple technique, like a classical regression, it has a lot of advantages. For example, we see the functional form and we can make sense of it as engineers. However, it might struggle with capturing extreme and complex nonlinearities and interdependencies in the database, such as the one that we are dealing with in this problem, with highly interbedded soil deposits, including mitigation and including soil structure interaction. It's a highly nonlinear problem that we expect the lasso to struggle with. So we started to look at other machine learning methods to deal with the data that we have with such complexity. And in our search for what is most appropriate to capture the extreme degree of nonlinearity in the database and help us at the same time reduce the uncertainty in our predictive model. Next slide. So there are innovations, advances in machine learning that have applications to this kind of problem. There are ways to uncover complex and extreme nonlinearity in the patterns. There are models that have flexibility in terms of the need for a functional form, and they can let us test model accuracy on dependent test sets, and this will help improve generalizability and robustness. And among the different options available, we selected the random forest model. Go to next slide, please. The random forest algorithm, it has the advantage of combining interpretability, accuracy, and efficiency. Now, this is not perfect, and if there is time, we can later discuss the problems with random forest. But some of the advantages here are that it reduces the risk of overfitting the data. It has a feature important analysis tool. It's great at capturing extreme nonlinearities and interdependencies in the data set. And it has added features that help us better visualize and interpret the results. And that can inform our design and mitigation models very well. So what is this random forest model? It's essentially an ensemble model that is built from multiple decision trees, and each tree learns patterns from a subset of the data. And then at the end, predictions are averaged to provide a final result. That's essentially the essence of random forest. Next slide. So first, before feeding all of our data into this algorithm, we need to check that the results are following what we expect from mechanics. And we did that. For example, I'm showing just a few cases here. We made sure, yes, we expect mechanistically that the settlement for a non-mitigated foundation to increase as the foundation's contact pressure increases, or as the slope of the liquefiable layer increases. So those checks were made. Then we give this data to random forest. Next slide. After which, we developed essentially 4 different predictive models for 2 scenarios of unmitigated settlement and then the ratio of mitigated to unmitigated settlement. And we considered 2 different models for first combining reinforced concrete and steel frame structures together, and separately for wood frame structures that had very different characteristics. And this helped us better manage the models and reduce the uncertainty. Next. So during this process, we had to feed the random forest with features. And so we started with 300 input features that made sense mechanistically, but we really didn't know which one would be most important. And so, no engineer wants a model where they would have to enter 300 input parameters in. So we had to narrow things down. This was later refined based on simplicity and practicality. We looked at which features were most important according to a random forest's ranking mechanism. And we made sure that they were physics informed and they followed trends from mechanics. And we could check the predictive accuracy on the test sets by essentially removing an input feature and seeing what the effect is. In all of these cases, we always also have to feed the machine learning algorithm with what is an optimum intensity measure. And I won't take your time with that. We have published plenty on this topic before, and I can come back to it if there are questions. But essentially, we gave the two most optimum intensity measures that were cumulative absolute velocity and spectral acceleration at a period of 1 second to the algorithm. And it used 20% of the data as tested. 80% of the numerical data was used as training set, and it iterated to come up with the best model. One more thing, the process was repeated 100 times to come up with the best model. And in this iteration, it used the test set to keep checking for the accuracy of the predictions. So now, after we had these final models, we compared the results. The predictions on the left are showing for the settlement of non-mitigated structure, and at the bottom, DGC settlement to non-mitigated. So on the left with the blue circles, you see this is the results of predicted from machine learning versus observed or the numerical data. So those comparisons are really good, but the real set is for the plot on the right. That's the testing set that was not used in the training of the model. And you see that the comparisons are still decent. The table shows more of the statistics in terms of R-squared, standard deviation, or RMSE, that are still showing reasonable comparisons and uncertainty in the predictions in terms of the testing set or testing data. Next slide. So here I'm showing a comparison of the uncertainty in our model with what is out there. So on the top is again standard deviation from our just a random forest model for settlement of unmitigated structures. I can only compare with settlement of unmitigated structures because there's no other model in the past with mitigation. And then the second row, I'm showing, if we had used the lasso instead, the standard deviation would have increased 2.91. So this is for natural log of settlement. So it has a big effect. And Bray and Macedo's model for settlement that used the classical regression. Our own model in the past, Bullock et al., that used lasso, you see 0.67. Now, if we use the Bullock et al. Model with our new data that now has stratigraphic variability in the profile, you would see a major increase in standard deviation. Next slide. Okay, so, and I would just go through this quickly. I wanted to show that this is one of the features of random forest that allows us to interpret the physical relationship between the input features and the final prediction of settlement. These SHAP values essentially give us a sense for how each input parameter contributes to the calculated settlement. For example, from the top to bottom of this plot, it rates it shows them in terms of order of importance. So CAV, or cumulative absolute velocity of the ground motion, had the highest importance. It has the highest influence on settlement predictions. And then after that, we have the slope of the critical layer, or the product of depth, relative density normalized by the thickness of sand layers, and so on. So we can see how important they each are and what's the polarity of their influence. Does their increase settlement or decrease settlement? And that's a useful feature for us to make sure that the patterns and the input features in the machine learning tool makes physical sense. Next slide. Okay, so the last step was to validate against case histories, and we were only able to find a very limited number of case histories that had CPT recordings available near building structures, and where we had reliable data. This is one case from the 99 Kochali earthquake. Next slide, please, where we had CPT recordings and the properties of the building present. We digitized the CPT traces and got the input features and went on to our machine learning based predictive model for settlement. We couldn't find anything with mitigation, so this is just comparing with the unmitigated settlement model. Next slide. And here I'm showing with the blue lines for two buildings in this case history, the fragility curves of probability of exceeding different settlement levels with the blue lines. And the dashed black line is our older model, Bullock et al. From 2019. And the red dashed line is what was actually reported from the case histories. So this is great. I mean, we are doing a little better than before now that we include stratigraphic variability in the profile and our calculations. But it's not enough for us to say for sure that we're doing better. This is not statistically significant. These are just two case histories, and it's certainly not enough to make any kind of statement. We need more case histories, and that is needed in the future to be able to truly validate. And I will end by saying that the models that I showed today were only based on settlement. Next slide. And in our papers, we also show predictions of foundation permanent rotation. But one important thing that happens, next slide, when we add mitigation is that settlement and differential settlement reduce, but accelerations amplify. And that can lead to damage in the superstructure. So in our new models, we are trying to provide recommendations for how acceleration on the foundation and the drift in the superstructure change, so that structural engineers can plan for it, and we don't ignore this increased demand in our retrofit of the buildings or in our design of the superstructure for structural engineers. Okay, so in conclusion, I showed that liquefaction assessment and ground improvement require detailed site characterization, in particular with high quality CPTs, to account for stratigraphic variability in the profile. I also showed that enhanced drainage seems to be a critical mechanism of mitigation for reducing both the permanent and differential settlement of the structure. And it's critical that we do what we can to minimize the likelihood of clogging in the field. At the same time, mitigation can amplify seismic demand, and we need to account for that in design. Now, the essence of this talk was to show that combining well-calibrated numerical simulations with physical experiments with innovations in machine learning can enable a new paradigm in mitigating geohazards through practical and accurate methods that account for highly nonlinear soil profiles and interactions in realistic sites and for realistic structures. Now, I will provide reference for different papers that have predictive models for ejecta potential, settlement, and tilt, and additional papers are coming out this year with more design guidelines for structural engineers related to acceleration demand in the structure after we mitigate the hazard. And there is clearly need for additional case histories with CPT recordings near structures, particularly when mitigation is involved, so that we can validate and improve these procedures. Thank you very much. Let's skip this slide. I can keep. This is a slide with problems related to random forest in case a question comes up. And here are some citations for those of you who are interested in this work. I'm happy to answer any questions, or we can move on to the roundtable. Thank you very much for your attention.
Shideh, thank you very much for this very interesting and nice presentation. I think we are running out of time because of the technical issues at the beginning, but I think we can address maybe a couple of questions. We have one from Alejandro in Michoacán. It's asking that the soil has a predominant period before and after liquefaction. In general, what is the approximate variation before and after liquefaction that you find, maybe in percentage?
So you're right. I can't tell you in terms of percentage, but there is densification that occurs. And I will need to look at some of our centrifuge experiments, especially that better capture the degree of this densification volume change after liquefaction, as well as fabric change. But I will have to look at, let's say, the transfer functions from surface to base to see how the dominant period, the fundamental period of the site changed. But you're right that we expect it to alter because of volume change in the profile.
Perfect. He's also asking you about your thoughts about applying transfer functions to. Oh, well, you already answered more or less that question. He read your mind, I think.
Yeah, I think that's a good idea to use the surface and base accelerations to look at the transfer functions and see how much shift in the fundamental frequency there is. I expect it to be noticeable, but yeah, I don't know what the percentage is.
Perfect. So Jessica Romero is asking, well, it's saying that it was a very interesting presentation. And her question is, I understand that only the horizontal component of the earthquake was considered in the study, although the vertical component is generally smaller in areas far from the source faults. How could it influence soil liquefaction and the distribution of soil layers?
Gosh, that's a really important question. I think there are disagreements on how important vertical vibrations are, especially in the topic of liquefaction. I'm personally of the belief that it should matter, especially when combined with when in the context of three-dimensional vibrations. If you only take vertical component alone, it may not affect things as much as the combined effect. Or when we have like one-dimensional or two-dimensional and then add the vertical vibration on top of that, the response and the volumetric strains, the intensity of shear and volumetric deformation in the soil, and the excess pore pressures, and therefore the extent that it would affect rocking of the foundation and such will be altered. We haven't been able to control this kind of problem in the centrifuge, and our numerical models are also not very well validated for answering this important question yet. So you can imagine having a controlled vertical vibration in the centrifuge in the direction of the centrifugal gravity is very difficult for the shaking table to simulate. But that's something that I think as a community we need to do more on, perhaps with other techniques like 1G shake table testing or just element testing with more variations in the loading path, so that we have better numerical models to answer the question.
Okay, thank you very much. A question from Alan Jonathan. He's asking, given the ratio between mitigated and unmitigated results has an R-square of 0.79 in the random forest model, what factors might contribute to the residual variance, and how could the model be improved?
Wait, so can you repeat the question? Let me also see is it in the chat bar?
Yes.
I can look at
in the webinar chat, not
okay.
the Q&A.
Okay, given that the ratio has an R squared of 0.79 in the random forest, for the what factors might contribute to the residual variance, and how would the model be improved? That's a really good question. This is one area in terms of, so this is for the test set, that the mitigation started to create more scatter in predictions of settlement. I don't know if the variance alone could be improved with more data. In fact, it might get worse. But one other problem that occurs with this kind of machine learning technique is sometimes, so 0.79 for this kind of complexity, to me, it's not bad. But you could say we could try different machine learning techniques to see if we could do better. I don't know if we would. And in fact, random forest sometimes has the problem of misleadingly showing a low degree of uncertainty and variance. So if we went to the truth of it, one of the types of machine learning approaches that is more of a state of the art, and we are trying to move toward as well, is deep neural network that might actually amplify the degree of variance, but it would be a more stable prediction. So I don't know if I'm answering your question. I don't think we can improve this variance that much because it is a complicated and uncertain problem. And in fact, if we go to more advanced types of prediction and machine learning, it might get worse, but at least it's more truthful.
Very good. Thank you very much. I think maybe one last question, and we move to the round table. There is a couple from Jose Luis Gonzalez. I'm going to choose the second one, which I believe is more interesting, and you have been working in the area of California. I think you will have something to say about it. So it is asking if a soil deposit have already liquefied in the past, can it liquefy again and affect the buildings in the surface?
Yeah, we repeatedly see that soils that have liquefied in the past will liquefy again and again and again. So yeah, liquefaction is a very weak method of redepositing and erasing the memory of the soil in terms of the geologic memory and the stability in the soil fabric. So if sometimes we see, let's say, small magnitude events that don't liquefy the soil, let's say magnitude 3 or 4, that maybe generate some excess pore pressures, but there's not enough energy to liquefy the soil, then that can increase the resistance of the soil to liquefaction next time. So seismic energy can increase stability in the fabric and resistance to liquefaction. But once you liquefy, for the most part, is erased that.
Like it's been
again, to some extent.
Thank you. Thank you very much for this nice presentation. I have here your certificate of recognition that we want to show, but right now, I don't know why my computer is becoming slower and slower, and I guess that if I try to share, it will crash. But we will send
Don't worry.
We will send this by email for you to have.
Thank you. It was my pleasure.
So again, thank you very much for this presentation, and I think